Welcome to today's presentation, where we're going to be going through a paper entitled Understanding Parameter Spaces Using Local Optima Networks, a case study on particle swarm optimization. This is joint work between myself, Christopher Cleghorn, and Gabriela Ochoa, and it's an interesting application of local Optima networks to understanding the hyperparameter space or parameter space of metaheuristics. In this case, we're going to focus on the PSO metaheuristic, but a lot of what we'll discuss here actually naturally extends itself to most metaheuristics. So one of the major challenges when utilizing a metaheuristic is finding the optimal, or at least near optimal, parameters for a given problem instance. And much computational time sometimes is required to actually find a good set of parameters. And with that in mind, the question is naturally asked of, is there a better or worse way of trying to tune parameter spaces or find good parameters? And is this approach in some sense fundamentally dependent upon the optimizer for which you're looking for good hyperparameters for? Now in this talk, we're kind of going to answer or focus on four specific things. The first is we're going to actually formalize the concept of a parameter space landscape as a natural specialization of the classical fitness landscape. Then we're going to also go through and try and demonstrate that LAHS can actually be used as an effective tool for understanding parameter landscapes, both from a metric and a visual perspective. We're going to use PSO as our case study in terms of the metaheuristics for which we want to tune the hyperparameters on. And then we're going to answer the more PSO-focused question of, does PSO's parameters form an easy or hard to optimize search space? The reason this is a question and the reason it's phrased in this way is a lot of existing research on metaheuristics has indicated that perhaps the hyperparameter space is actually somewhat easier than one would have anticipated. However, in this study, we will see something that is perhaps somewhat contrary to that earlier finding in the case of PSO, and potentially more broad in the realm of metaheuristics as well. So let's start with being clear by what we mean by a fitness landscape, and then we'll go through to the specialization for a parameter landscape. A fitness landscape, at least in this case, we're going to just talk about it in a discrete space context, is a triplet S, V, and S, V, and F, where S is simply the set of elements in your search space. V is your neighborhood function that would just take an element from your search space and map it to all possible connected neighbors based on whatever distance function you're using to define if an element is or isn't in your neighborhood. And F is the underlying fitness function, which would map an element or a candidate solution in your search space to some real value. Now, while a parameter landscape is inherently a type of fitness landscape, a specialized definition is going to be presented now because it focuses or draws focus to aspects that we think make discussing parameter landscapes somewhat more intuitive, specifically with the intention to draw a better focus on the interaction of the candidate solution. So in this case, a candidate solution would just indicate your hyperparameter choice, as well as the optimizer, as well as the underlying objective function. So there's these kind of three movable components that one has to consider, and by making a specialized case, it's a little easier to try and disentangle their relationship amongst each other. So our parameter landscape is defined, at least in a discrete context, as this tuple containing 6 elements. Now, it's actually much simpler than what this tuple may suggest, but it's worth kind of breaking down each of the individual components. Here, F is the underlying objective function being optimized. So before F was used to indicate the fitness, this F here is being used to actually indicate the actual underlying objective function we're trying to optimize. Say you're trying to optimize ACLI or restringent or something like that. And this optimization is happening over the domain D. So this is an indication of the search space of the optimizer as opposed to the parameter landscape itself. And furthermore, it's about the underlying objective function being optimized over domain D of algorithm A. So that's what the A is indicating, or which algorithm are we using. Is it a PSO? Is it a differential evolution approach? Is it a genetic algorithm? And so on and so forth. And then we have C, which is our set to indicate all possible control configurations that we would consider for the given algorithm and the given problem instance. And then we have our classical neighborhood function. We're just distinguishing it slightly from the earlier neighborhood function because it's relative to C, in this case being the set of all control parameters. So basically, from any given control configuration, what are the set of neighboring control configurations? So very much in line with the fitness landscape definition. And then last, and probably the most important, is P, which is our performance measure. So basically, P is parameterized by F, A, and D, where F would indicate obviously the objective function you're optimizing, A is the algorithm using, D is the search domain, and C, that is the parameter that's basically fed into this function P, is the control configuration that you're actually considering. So the way in which we'll typically view a parameter landscape is that F, A, and D are held fixed, and we're going to vary C to try and get a visualization and a better understanding of what the parameter landscape itself looks like. Now, something that's very much worth paying specific attention to is that in our case, when you're trying to analyze the parameter landscape of a stochastic optimizer, in this case PSO, but the same would apply to many metaheuristics, P is not a scalar. It is rather a distribution of possible performance values. That's because on different runs of our algorithm, even on the same problem instance and for the same set of configurations, we may get a different outcome, as is inherent to the nature of stochastic optimizers. Now, we're going to focus on just the expectation of P, so basically the expectation of the performance distribution. That said, it's worth being cognizant of the fact that there are perhaps other aspects of this performance distribution that are worth actually studying. So PSO is what we're using for our case study here. In this context, just for the sake of clarity, PSO is a stochastic population-based search algorithm originally developed by Kennedy and Eberhardt in 1995. We're actually going to be considering the slight alteration by Shih and Eberhardt in 1998, I believe, where we just included the inertia weight to the original PSO structure. Now, the salient aspect of PSO that is actually relevant to this talk, so I'm not going to go through the full definition of PSO, but the salient aspect that's relevant to us are the three important control coefficients of PSO, namely the inertia weight, the cognitive coefficient, and the social coefficient. So these are the three real valued coefficients that we often have to tune when we're using PSO to solve an unseen problem. Now, the issue is that the optimality of PSO's performance is very sensitive to the precise combination of these three values that we select. One notable observation made with regards to this is that when certain theoretical properties are not satisfied in terms of the selection of W, C1, and C2, you end up getting quite poor performance. So you basically enter a failure state for PSO. And in this case, that is a situation where you fail to meet the order 1 and order 2 stability criteria. But even past that kind of hard bound of performance and failure, there is also inside that region where that criteria is met, there's still many choices to be made. It's not a negligible size region. And what works best for one function is often not the same as what works best for another objective function. Now, in this work, as we stated earlier, we're going to utilize local Optima networks as a way of visualizing and understanding or analyzing the PSO's parameter landscape. So for this work, we're going to be using the standard LON, the monotonic LON, as well as the compressed monotonic models. In reality, the LON and the compressed monotonic LON are where we do most of our analysis, but the monotonic LON is a convenient middle step. Just informally, so everyone has a sense of what we mean by a LON, this is a little bit informal. If you want more rigorous detail, I recommend checking out the paper. But basically, each node in a local Optima network is a local Optima, where in which we define a local Optima to be one in which there are no elements in its neighborhood that are in fact strictly better than it. In this context of a local Optima, we say that there is an edge between two nodes if there is a non-zero escape probability from one node to another. By that means, if I started at one node and I apply a random perturbation, and then from that point I apply a hill climbing type algorithm and I settle in another location, the odds of me ending up in that other node would be an indication of the weight that would be applied to that edge connecting those two nodes. So if there's a zero probability, then we don't have an edge, but if there's a non-zero probability, we have an edge, and the weight of that edge is dictated by that escape probability. Monotonic LONs are a subtle tweak in which we only actually are interested in the non-deteriorating edges of our LON, basically the path you would likely follow if you were trying to actually traverse this local Optima network in the seeking of a good Optima. And then lastly, we have the compressed monotonic LON. In this situation, it's just a compressed version of the monotonic LON where connected nodes, so basically we say nodes are connected if they are connected to each other via an edge, a single edge. And if those two nodes that are connected via an edge have equal fitness, then these nodes are contracted together and the corresponding edge weightings are updated accordingly. So it's really a compression mechanism applied to the monotonic LAN, and the premise being that if there's two or more local optima that are right next to each other in the search space, we can kind of contract them to a single basin, because if you landed up in one, you may as well have landed up in another, to get a better sense of what the real search space is actually looking like. So with this in mind, we have to figure out what our set C is in terms of what is our search space, what are we actually analyzing. So for our case, C, so the set of all control coefficients that we're considering, is generated considering the intervals W between -1.2 to 1.2 and the sum of C1, C2 from 0 to 5, where in this case we're considering C1 and C2 to be equal, and we're going to sample points every 0.1 along W and C1 and C2. So this results in the set C being 1,250 possible configurations, and each of them are tested on each of the 26 considered benchmark functions 30 times, and we're going to be using that distribution for our analysis and construction of our LANs. Now that region in equation 1 was chosen as it satisfies the conditions for order 2 and by implication order 1 stability. For PSO, it's slightly larger than that stability region, so it gives us a good sense of where the parameters are in and out, and so that we're not completely confining ourselves to the theoretical consideration, but we also are looking in the right place in the parameter region for the study. So in a place where people would likely actually be picking parameters for PSO. Now, what are some of our findings? Well, the first and most kind of shocking observation is that the parameter landscapes of PSO applied to different functions are far from trivial. So even if we look at the normal classical visualization on the left, where we have C1 and C2 along the one axis and W along the other, and we have the fitness indicating our Z axis here, you see that we have this relatively flat region. By the way, this curve kind of corresponds to that order 2 stability criteria I mentioned earlier. And at first glance, this maybe doesn't appear to be that challenging of a search space. However, if you actually look along this edge, you see there are many false optima. So there's many local optima that you could actually get trapped in if you were just kind of directly searching the space. And actually, if we try and model this as a local optima network, we actually see the situation is even far more complex than the visual illustration on the left would actually entail, where we have many local optimas in the search space. So generally speaking, it's roughly 10% to 20% of all of the parameter configurations ended up actually being local optima, which tells us that this is not a trivial search space. What we see on the right here is the compressed version. So it's just kind of laid out a little bit nicer, and we don't have any of the deteriorating edges present. But you see here this red dot indicates our global sink, but we have multiple of these blue dots scattered around indicating we have these local sinks where you could end up getting trapped. So basically, if you were to try and search in the search space, you would end up getting stuck in these suboptimal configurations quite easily. So for many of these starting locations, you would actually, if you proceeded with this perturb and hill climbing procedure, you would end up getting stuck in one of these non-optimal sinks. Now, this kind of structure occurs across multiple of the functions. The one thing I should make a statement about this Ackley case even, so Ackley being the underlying objective function we're considering, is that the compression doesn't substantially alter the structure. The spacing of the visualization makes it look like there was a bigger change, but there was not very much compression taking place. In most of the objective functions we consider, there was not actually much compression, and that's even under the consideration where we have a lax definition of equality, wherein which we say that two fitnesses are seen as equivalent if they're within an epsilon range of each other. In this case, epsilon was 10 to the minus 5. You would expect there to be a little bit more contraction, but it's not something we observe generally across all of the functions. In fact, there are only 5 of the functions that actually obtain any kind of compression, with most of them being negligible except for one that I'll show you shortly. Just moving on to another example, this is the egg holder function. And again, you see that the top part of this landscape is relatively flat, though a lot more rugged than it was in the Ackley case. So already an indication that things do not stay the same across different objective functions. But you'll see that this cusp over on this, where I'm pointing this little hand, is considerably more raised than was the case in Ackley, indicating that there's a slightly different mechanism happening inside this internal, this larger sink, if you will, that the structure at that edge is substantially different between the two. Now, in this case, we see that the LON is also relatively complex, in which we actually see that there's more of an attraction force towards a local optima than we would actually have liked. And when we go to the compression, we see that you have many of these local sinks scattered around where you would end up getting stuck. And actually, the odds that you end up getting into one of these local sinks, which you can indicate or see by the size of the blue dots, is actually going to be larger. Particularly this one blue sink is going to be considerably larger than the odds of ending up in the global sink, which is obviously not ideal. If we move over to the HyperEllipsoid function, we see a slightly different structure present with the LON. We see actually we have multiple global optima. However, as soon as we apply the compression mechanism, we end up getting a constriction down to a single local optima, a single global optima, which is clear evidence that all of the global optima present in the original search space are actually directly connected to each other. So they're not scattered across the search space. In this specific case, the HyperEllipsoid, you actually had a relatively strong likelihood of ending up inside the global sink, but it is actually one of the outliers. So even though it's stronger, I'll show you shortly now with some of the statistical measures or some of the measures that it's more likely, but it's not overwhelmingly so. There's a couple of questions at this point that I think are worth answering, and to do so, I'm going to use this abbreviated table from the paper. The first observation, if you look here, we record the number of global sinks, and after the compression, every objective function results in a single global sink. So that's a property that seems to appear to be consistent over all benchmark functions considered, at least for PSO, but it is a strong indication that it's potentially a likely property of the algorithm itself. Perhaps in some situations you may end up with more global sinks, but it does appear to hold relatively strongly. The next aspect is this FR, and this is a relative funnel size measurement. And this is kind of a very clear measurement of how likely it is for a random point in that search space to actually be connected to the global sink. Now, if we go back and just look at some of these visualizations, even on the left on the 3D side, it's not surprising that this should actually be relatively large, because there are many points that you would assume in these regions that are actually going to fall within this kind of larger hole in the search space, or this larger macro level type basin. And that is actually exactly what we see in the context of FR, where the actual relative funnel size is pretty large. In many cases, it's above 40%. In the highest case, it's slightly above 50%. Across most of the objective functions, indicating that it's quite likely that you can potentially reach the global optima from your start location. There are some exceptions, like for example F25, where it's only 15% and 16% in the case of F18, but for the most part they're relatively large funnel sizes. Now this might give you the impression that it's maybe not that hard to search, and that's almost the first gut reaction one may get when you see the 3D visualizations. At first glance you might think, oh, that can't be that hard to search, or this might not be that hard to search, because we have this clear downward trajectory present in the search space. However, if we start considering things in a more fine-grained level, and we consider what the strength of suboptimal sinks is versus the strength of suboptimal sinks are, we see a slightly different picture. So just kind of informally, the way you can interpret this strength is basically how likely is it for you to actually end up in the optimal sink from a random start point. So if you were to apply hill climbing mechanisms and so on and so forth, how likely are you to actually end up getting to that global sink? And on the other side of the coin, we have the strength suboptimal, and this is how likely are you to end up landing in any of the local optima. And actually, if we look across here, it's quite a grim picture, where the odds of actually ending up getting at the optimal, or the optimal sink, is pretty low. In most cases, it's below 10%. There are a couple of outliers like F11, where it's 22%, but by and large, it's a very low score. I mean, in the smallest case, you see 0.4, so only 4% of ending up there from a random start location. So it's not particularly great. Whereas we have this very high chance of ending up in a suboptimal sink. So the question one has to ask at this point is, okay, fine, it's not trivial to get to the global optimum, but perhaps the local optima are sufficiently good that this really isn't an issue in practice. However, what we actually found is that the average difference in fitness, so this AVDIF fitness, between the local optima sinks and the global optima sinks is far from negligible. In some situations, it's not so severe, but in many of these functions, for example, just looking at f3 here, we see that there's an average difference of 3 to the power, or 3 times 10 to the power of 10. Now that's an incredibly large difference in fitness. So it means that even though you ended up in a local optima in terms of performance, it was actually a horrendously performing configuration, implying that even though it's a local optima, it's a considerably bad optima, which means that this finding that the odds of getting to the actual optimal strength is actually going to be very impactful in terms of the resulting performance at the end. I mean, even if you look down all the way at this F22, we see that the difference there is 3.97 times 10 to the 12. So you're talking about a trillion difference in fitness value. Now, clearly F23 has a very large fitness rate for this to be possible. However, this is a strong indication that there's a substantial difference between the local optima sinks and the global optima sinks. Furthermore, the variance across these differences is pretty high. So the distance between my optimal sink and the suboptimal sinks in terms of fitness is also substantial. So it's not even a matter that it's a clear way of distinguishing between local and global. We have a huge degree of variance across this average difference. And all of this combined gives us very strong evidence that PSO is actually not a very easy, or does not have a very easy hyperparameter space to optimize. Now, this isn't to say that this is not something that is present in other metaheuristics. It may well be the case, but this is demonstrable evidence that the LONs are very good at actually exposing this intrinsic structure, in which it's actually quite challenging to optimize these search spaces, and we probably should consider either algorithm-specific type tuning, which is obviously not ideal, or have a way of indicating or predicting how hard it is to tune a specific optimize and make decisions from that point onwards. So in summary, what have we achieved in this paper? Well, the first thing is we provided a brief formalism for investigating parameter landscapes, and there's a different number of ways that can perhaps be used, particularly because you have a distribution, we can do more sophisticated statistics on it. The other is that we have demonstrated that local optima networks can be effectively utilized to visualize as well as analyze the parameter landscapes. And it was actually found that despite earlier research in the realm of parameter landscape analysis suggesting otherwise, that parameter landscapes can be of significant complexity. Earlier research in hyperparameter tuning indicated that in many situations, the landscape was actually comparatively trivial. That is not at all what we find in the case of the metaheuristic that we studied in this work. That could occur from two things. The one is that a lot of the earlier research that dictated the fact that this landscape may be simple was considering the scores aggregated over benchmarks as opposed to on individual functions, which could be a bit misleading about how hard it is to tune for your real-world problem that you encounter, as well as the fact that it didn't deal with the interaction between multiple hyperparameters in a very thorough manner. So there's two aspects that could explain that discrepancy, but it's definitely very enticing from a further work perspective because we can potentially codify different algorithms in terms of which are easier and which are harder to actually find good parameter configurations for. And this is quite a considerable step up from just say sensitivity analysis where you say, well, this region works well. Oftentimes you want to find the best possible configurations of these algorithms. And this is a good way of trying to measure that across your known metaheuristics that you may consider for real world problems. And furthermore, in a more PSO-centric fashion, it was found that the PSO landscape is fundamentally influenced by the underlying objective function, and that each landscape itself was far from trivial in terms of searchability. Now, that's not to say that this will hold for other metaheuristics, but this is a good indication that it's most certainly not a guarantee that you will have a nicely well-behaved parameter landscape for a different evolutionary algorithm. So that brings us to the end. We thank you for your time.